Hello, my name is Gal. I'm a graduate student at Tel Aviv University, and today I'll present our work, Z2P, a neural method for instantly visualizing point clouds. This work was done in collaboration with Rana Hanocka from the University of Chicago, Niloy Mitra from University College London and Adobe Research, and my advisors, Giryes and Cohen-Or² from Tel Aviv University. Z2P is a fast neural technique to instantly visualize point clouds as if they were 3D meshes. Our method avoids the need for a full 3D reconstruction by projecting the point clouds into a 2D image and using an image-to-image translation technique to produce a naturally looking visualization. Z2P allows for basic visualization controls like view direction, light direction, and color, and can also be extended to more complicated controls such as material specularity and roughness. Currently, point cloud visualization techniques can be roughly divided into three categories: splatting, surface reconstruction, and hidden point removal. Splatting in a nutshell is placing small circular disks at each point in the point cloud in the direction of the point normal. This is usually followed by a screen space smoothing operation to merge the disks together into a continuous surface on the image plane. On the one hand, splatting does not require a reconstruction of the entire surface, but on the other hand, normals are not always given and may be hard to estimate, especially for noisy point sets. Also, the disk size may be hard to set, leading to holes in the visualization as seen here. Second is full 3D surface reconstruction. The upside of surface reconstruction is that by having the actual mesh, you can use almost any 3D engine to render the shape. But the downside is that surface reconstruction is a difficult problem all by itself, as most reconstruction algorithms require clean point clouds containing points only from the surface of the shape, together with oriented normals, in order to work properly. All of which are not trivial to obtain in the real world, and especially for point clouds generated by neural networks that do not have any information whatsoever. Lastly is a method called hidden point removal from a paper called Direct Visibility of Point Sets by Katz et al. This paper mostly discusses the problem of filtering out occluded points, but also suggests a method for computing an explicit triangulation from a single view direction. This method is pretty elegant and fast to compute, but has a hard time handling noise as any explicit triangulation technique, and is not guaranteed to produce closed surfaces as seen here. Our method is pretty straightforward. We first project the point cloud into a 2D image plane from a desired visualization direction. Then we pass the 2D Z buffer or depth map into a neural network that is trained to convert Z buffers into surface-like visualizations. Our network is also conditioned upon the visualization parameters to allow control over color and light. To train the network, we generate a synthetic database made up of pairs of meshes and corresponding point clouds. Each point cloud is sampled from a uniform distribution over the mesh surface, and both the meshes and point clouds are rotated and colored randomly to enrich the data with diverse examples. The training procedure is as follows. For each training step, we render a mesh using Blender, together with randomized rendering parameters. This rendering is regarded as the target ground truth visualization we seek to produce using the neural network, and the randomized rendering parameters are saved as a 6-element long vector of RGB color and light position coordinates. Then we project the corresponding point clouds from the same camera angle to produce a point Z buffer and use it as input to the neural network. We train the network to output the corresponding target rendered ground truth mesh And lastly, we condition the network on the rendering parameters in order to gain control over the visualization parameters at inference time. Here you can see the input and output of our network for a particular shape. On the left is the input point Z buffer, where the intensity of each pixel corresponds to the depth of each point from the image plane. And on the right, you can see the result of our network. Be aware that our network is not explicitly designed and trained to handle videos, meaning each frame is processed independently by the network. Here you can see the effect of the light direction coordinate control over the visualization output. The yellow dot corresponds to the input light coordinates. Notice how our network is able to create self-shadows of the thumb onto the palm of the hand when the light source is set at an appropriate location. A similar setup is presented here on this different shape. Observe how our network is able to produce longer range shadows, which appear on the area below the chair when the light source moves in an angle above the chair. Our basic controls allow for setting the color of the visualization as well. Here you can see the result of our method when changing the input color control. Notice how the geometric structure and shadows remain constant, while the only thing that's changing is the color of the visualized shape. Point clouds generated by deep learning methods are particularly interesting as they do not contain any normal information and tend to have points inside the shape's volume, both of which screw up common full surface reconstruction alternatives. This is an example generated by a work called point flow by Yang et al. When trying to estimate normals and run common surface reconstruction algorithms, Poisson reconstruction leads to a surface containing many artifacts due to incorrectly oriented normals and points inside the shape's volume, and ball pivoting has a lot of holes, also due to incorrectly oriented points and the uneven point distribution. On the contrary, our method is able to achieve a better visualization without the need for surface reconstruction, as seen on the top right corner. This example was also generated by another deep learning method called ShapeGF by Kai et al. Again, common reconstruction techniques tend to fail at certain areas for the same reasons seen in the previous slide, while our method is able to produce a more accurate visualization. Also, observe how our method is able to produce an accurate shadow in the shape of the wing on the ground plane. Another advantage of our method is runtime. The fact that our method is faster to compute makes sense, as only a single view visualization conveys less information than a full 3D reconstruction. Note that currently the slowest part of our method is projecting the points into the 2D plane and filtering out nearby occlusions. We believe that this part of the method can be further optimized and sped up significantly. Other than the projection, our method takes a constant amount of time to run, as it is only done by a single forward pass through the network. While other reconstruction techniques usually depend upon the number of points and the desired output resolution. Note that these runtimes are measured on the same machine using the Open3D Python library, and runtimes may vary a lot depending on the machine and number of points and the desired output resolution. Our network architecture is similar to a unit network with an hourglass structure and skip concatenations. We swap the batch norm layers in favor of adaptive instant normalization layers, or ADIN for short, in order to condition the network on the rendering parameters. ADIN layers have shown impressive results in style transform application, which are similar in nature to our objective of having enough control over the shape, color, light, and material, while still rendering the same geometry or content. In the paper, we also show an ablation over passing the rendering controls as part of the input features and try to explain why that's worse. In addition, we pass in position and encoding features as input in order to improve the shadow quality, as will be explained in the next slide. In this example, we slowly raise the airplane point cloud in a vertical direction, which gives the appearance of a plane taking off. As vanilla CNNs are translation equivariant, a naive CNN always renders the shadow right below the plane, no matter where it is in the input image. But on the contrary, when adding positional and encoding features, the network is able to tell where the ground plane is absolutely in the image and always render the shadow there. We tested our method on a variety of point clouds out of the training distribution in order to show generalization. Recall that our method was only trained on point clouds sampled from a uniform distribution over the mesh. In earlier slides, we showed successful results on point clouds generated by deep learning methods, which have a very different point distribution than the one sampled from the meshes. Apart from that, we also evaluated our results on point clouds produced by real scans, as seen in this slide. One particular scenario is of point clouds that were scanned only from a single view direction, like the top example here, meaning they don't form a closed shape. This type of point clouds cannot be reconstructed with Poisson reconstruction, as Poisson assumes a closed surface to begin with. And the fact that our method is able to handle such point clouds as it projects them into a 2D view can be useful for real-time visualizations of 3D point clouds from scanners. As point clouds that come from real scanners may contain various levels of noise, depending on the scanner quality and object material, it is interesting to observe the effect noise has on our method compared to others. Here are two competing visualizations of the top left point cloud. Splatting becomes difficult at higher noise levels as normal estimation becomes a lot more inaccurate, which is noticeable through the splat's shading. Similarly, HPR, or hidden point removal, also suffers from the noise as it performs an explicit triangulation of the noisy points. Our method outputs a better visualization, but still contains some amount of noise from the input point cloud. In fact, we can retrain our network on a new dataset containing noisy input point clouds together with clean meshes. This is able to suppress the amount of noise in the visualization and produce a much smoother result without any dedicated denoising step. As stated earlier, our method nominally allows for basic control over the color and light direction. But this is only a consequence of the type of rendering controls we randomized and input as the setting vector to our network. In this last experiment, we experimented with more controls, specifically the material roughness and metallic specularity. We trained the network on a newly generated dataset where we also randomized two new scalar values between 0 and 1 that were concatenated to the original setting vector and used as the material roughness and metallic specularity of the ground truth rendered meshes. In this video, we slowly walk on the roughness specularity simplex and show the effect it has on the output. Similarly, here we see possible combinations of both attributes and the effect they have on the visualization output. This experiment comes to show that our method can also be useful to other desired visualization characteristics, that are similar to style transform, as long as they can be modeled by a rendering engine in order to generate a data set for the network to be trained on. The projection into 2D does not come without limitations. When points from different surfaces are too close to each other and have similar depth, they may be rendered as the same continuous surface, as they are indistinguishable by our network. Note that this limitation may also apply for some 3D reconstruction algorithms, more specifically when the input point cloud does not contain any normal information and the normal orientation has to be estimated. One future work direction we believe may be interesting to check out is estimating a normals map instead of directly the color like we do now, which will allow the use of matcaps for shading. We ran a minor experiment trying to replace the ground truth target rendering of meshes with a normal map also produced by Blender. Even though some results were not bad, as seen here, in many other examples, our method failed to produce an accurate normals map, which led to bad visualizations. We believe that with certain changes and normal dedicated losses, this objective can be achieved and open the door for more interesting material properties. In summary, our method is able to visualize point clouds without reconstructing a surface. Our method is simple and effective, as it does not involve normal orientation nor surface reconstruction. Our method is suitable for point clouds from a variety of sources, many of which it was not trained on, and can be extended to other visualization controls, such as material properties. Thank you for listening. Our code and data sets will be released very soon, and please check out the paper and website for more information.